Hello and welcome to this new video where we are going to discuss mathematics and physics on the board. In this video, what we are going to do is basically show how we retrieve something called Maxwell's relation in thermodynamics from the exterior calculus. And the bottom line here, this is actually a very, very powerful technique that allows to really retrieve very important relations between measurable quantities most of the time in thermodynamics. So here I'm just going to show one example, but actually this can be applied for any free energy or what are called thermodynamic potentials or even Massieu potentials, depending on which book you study and kind of which school you belong to. So basically that's what we're going to do. Okay, so as usual, let's set a little bit the stage. The only ingredients we need to know here are a bit of exterior calculus, so I'm going to put some link here if you want to explore some of the things we are going to use here, not very much really, and then a bit of thermodynamics, and in particular simply the first law of thermodynamics, which tells us for a simple compressible system. So a simple compressible system is a system whose thermodynamic variables, so the thermodynamic variables of interest to us, are going to be pressure, temperature, amount of matter, and volume. And that's it. So these are basically so-called simple compressible systems. And basically from there, we can move on to express this first equation that tells you that the variation in internal energy is going to be minus P dV plus TdS plus mu dN. And again, this is all in what is called the receiver convention, where all of these quantities, if they are positive, it means that the system has received energy. Now, equation 2 is actually just stating that U is a function of the thermodynamic state. And basically, that's where we are going to start from. So what in substance equation 2 is saying is that I can view U, and I'm going here to write the variables of interest. So S, V, and N is a zero form. Okay, so that's what it means to be a function. Is basically you are a zero form in the context of exterior calculus. And then once I'm there, I'm going to say, well, therefore, I can interpret D, the exterior derivative, and imagine that the du here is the actual exterior derivative. And so if that's the case, I also know that du has to be equal to du dv dv plus du ds ds, and then plus du dn dn. By the way, I forgot to say, some people may take issue, a bit nitpicky, may take issue with the fact that I'm imagining the first law to apply with varying numbers of particles or in composition. I don't care. This equation is valid. That's the only thing I'm caring about. So, so basically, we've got this particular equation. And what we are going to do here, and that's going to be important, is say that, let's say this is 1 prime. And we are going to say that 1 prime is obviously has to be equal. They are saying two different things, okay? But they are actually about the same quantity. And so the only possibility for both to hold together is actually for the individual terms to be equal to each other. So, so 1 prime equals 1 if and only if we end up with minus P is equal to du dv, then T is equal to du ds, and finally mu, which is the chemical potential, is equal to du dn. Now, I didn't specify. Usually I'm very kind of annoying about this. which variables you need in principle to keep fixed. So for example, here you need to keep the number of particles and volume and entropy fixed. Here, this would be volume and particle number, and here that would be entropy and volume. Okay, so you need in principle to specify who is going to be kept fixed, but here I'm kind of skipping over that little aspect. Okay, so that's what we have. Now, the next stuff I'm going to use from exterior calculus. So I'm going to say from exterior calculus. Again, that's the theorem we had seen. We have that d to omega equals 0 for any omega, so for any form. So here that belongs to lambda, whatever, like I'd said n minus 1, right? So yeah, so in our case, what that means is that d to u is equal to 0. All right, so that's great. But now what I need to do is take the exterior derivative of du here. So what I'm going to do is basically write it here. So I've got yeah. In fact, I didn't have, to be honest, to actually write this. It's a bit silly. But let's see. So I can just start from 1. So here, this is just something that we can derive and some relation that are kind of interest. But they're not going to be necessarily useful for what we have to do here. So from equation 1, that's enough. We need to have, so we've got du is equal to, so we've got minus dp and then wedge dv, and then plus dt wedge ds, and then plus d mu wedge dn. Okay, so that's what we have. Now, what I'm going to write is, remember that dp here, I'm going to assume, because this is at least I need to know that this is a partial derivative of u, and that u is a function of sv and n, therefore p is going to be a function of sv, a natural function, if you will, of sv and n, okay? So the only thing I can do is basically write dp here by using the same exterior derivative formula as here, but then I don't need necessarily to complicate myself. I know that the part in dv is going to contribute to 0, so I'm not going to put it there. So what I end up with is basically du is equal to, and so let's put the minus sign here, and then we are going to get dp ds ds plus dp dn dn, and then wedge dv. And then here I do the same for dt. So we've got dt dn dn plus dt dv dv. Again, I don't put dt ds because wedge ds is going to be 0. That's wedge ds. And then plus d mu dv dv plus d mu ds ds, and then we've got wedge dn. So now what I'm going to do is simply try to group the terms together. So for example, let's say we've got a ds dv. So let's actually look at, so let's look at ds dv, for example. ds wedge dv, so it's going to be factorized minus dp ds, okay? And then we need to find another one here. So that's minus dp ds, and then minus, if I'm not mistaken, dt dv. Okay, And here what I've used, that dv wedge ds is equal to minus ds wedge dv. Let's continue. We've got a dn dv, so plus dn wedge dv. So dn wedge dv, we've got minus dp dn. And then what else do we have? So minus dp dn, and then here we've got again, hold on, it says dn dv, so I've got one here, and that's minus d mu dv. And finally, the last one is the ds dn. And ds dn is going to be, so we've got d mu ds, and then here ds here plus dt dn. Okay, so here again I've got ds dv, dn dv. I'm just trying to see if I made a mistake somewhere. And this basically has to be equal to 0. And the only possibility for this to be equal to 0, given that these are kind of basis vectors that are all independent from each other, is that they are individually equal to 0. This is equal to 0. This is equal to 0. And this is equal to 0. Okay? And so basically setting these triplets of equations to 0 is what we call Maxwell's relation, because you see they relate the derivatives of some of the quantities here to their, oh, I forgot one actually, sorry, apologies. This one, it could be minus here because we had, where is it? dt dn here, and it was dn ds, so I need to switch to get a minus sign, so there was a minus sign here. But basically that's it. So these triplets of equations are Maxwell's relations. And again, the reason why they are super useful is because they relate thermodynamics quantities with each other, or at least the partial derivatives of thermodynamic quantities with each other. And this is super useful to actually draw otherwise kind of complicated conclusions to draw. To calculate effective things like the specific heat of some material, not necessarily in isochoric or isobaric conditions and so on. So basically that's it. That's the spirit of it and how you do it very fast. In fact, this part was almost unnecessary. It was only necessary to kind of tell and convince ourselves that these variables would be functions of S, V, and N. But otherwise, this part could have been skipped, and we could have directly moved onto this, and then voila, it would have been done. Okay, so I hope you found this insightful. Again, this is relating plenty of interesting quantities with each other, and this is used in many different areas to draw various conclusions and so on in terms of measurements or theory. Okay, so if you've got any questions or comments about this, by all means, do let me know in the comment section, and otherwise, see you in the next video.